Hello everyone, my name is Grigori and I will be presenting our work on coherence modeling with RST features. First, I will introduce the concept of coherence modeling and rhetorical structure theory, as well as provide the background on previous work. The goal of coherence modeling is detecting the aspects of the discourse that make the text clear and easy to follow. This usually goes beyond local aspects like grammaticality. Instead, a well-written coherent text typically exhibits a clear and logical high-level structure between its constituents, like sentences and paragraphs. Therefore, an ability to utilize the discourse information will be of high utility for automatic text correction and enhancement tools. Looking at the provided example, we can see that while the text on the top is certainly readable, the correct example on the bottom is much easier to follow. One reason might be their organization. In the bottom text, the description of events causes always precedes the event's results, while in the top text, the ordering is opposite. We now review the rhetorical structure theory, RST for short, which is the tool that allows us to capture the document discourse information. An RST analysis of the document is performed by building a constituency tree over its list of elementary discourse units, EDUs for short, which are non-overlapping clause-like sentence fragments acting as the leaves of that tree. Each node in the tree denotes the nuclearity, being the relative importance, and the discourse relation between its children. In the example provided, there is a discourse relation background between the first EDU and the union of EDUs 2 and 3. EDU 1 is the satellite of that relation, whereas EDUs 2 and 3 are the nucleus. We now review the previous work. A well-known approach for coherence modeling is based on centering theory, involving creating entity grids that encode salient entity transition patterns across sentences. In the example on the bottom left, the rows are sentence IDs, columns are the entities present in the text, and the cells denote whether the given entity is a subject, object, or it is missing from that sentence. Roughly, this allowed the authors to represent how frequently the discourse shifts its focus, and if too frequently, this signals that the discourse is probably incoherent. They learn linear models to rank the coherence of original text against their sentence permuted versions, of automatic textual summaries across different summarization systems, and of same topic essays written by English language students. To improve on their approach, the follow-up work successfully extended entity grids with discourse relations that entities participate in a given sentence. However, these approaches have certain limitations. First, only the RST relations tied to specific entities were used, not the overall tree structure. Second, the tasks that models were tested on involved either synthetically generated data or text produced by non-native English language students, making these texts not a perfect proxy for evaluating coherence of a typical English text. Our goal is to develop a neural coherence modeling approach that would incorporate the document's full discourse structure and test this approach in a more realistic setting. Now we propose models that apply the RST tree of a document to evaluate its coherence. First, we use an off-the-shelf RST parser to produce the RST structure shown in the bottom left. Then this tree is encoded into an embedding using a tri-LSTM neural network that traverses the tree bottom-up. On the right, we show how the recursive step is performed. For each node within the tree, the network is recursively called on both the left and the right subtree, producing representations in the form of the output, hidden, and cell states. This, together with the learned embedding for the discourse relation, are then used to compute the representation for the parent node, consisting again of a hidden and cell state vectors. At the leaf nodes of the tree, there are of course no subtrees to process, but rather the EDU text itself. To this end, we propose two approaches. First, we can initialize the leaf states with simply zero vectors, as seen on the left. We will refer to our model that utilizes this approach as simply RST-Recursive. Second, we can learn textual EDU embeddings using a separate LSTM that encodes the text in a feed-forward manner to produce hidden and cell state embeddings for the leaf nodes. This process is depicted on the right part of the figure, and we will refer to it as RST-Recursive plus EDU. The second approach allows us to incorporate the textual contents of the document into our model. On the other hand, the first approach will let us test if the RST discourse structure itself is sufficient signal for classifying textual coherence. We now describe how the document representation and coherence are computed. Once the tree is traversed up completely, a document embedding is generated by concatenating the outputs of the left traversal and the right traversal of the children of the root node. This vector embedding is processed by a fully connected layer, which produces logits for the softmax classifier that assigns probabilities to each class of the coherence, which will be described in the next section. Lastly, we also considered the previous state-of-the-art method, namely ParSeq. ParSeq uses free LSTMs to encode coherence at the sentence, paragraph, and document levels, where the last, paragraph LSTM, operates on a sequence of documents paragraph embeddings to generate the document representation. This document embedding is similarly passed to linear and softmax layers for classification. Finally, we describe our experiments and results. For evaluation, we applied the recently introduced Grammarly corpus of discourse coherence. It contains documents from different genres labeled by expert annotators on 3 levels of coherence, being very incoherent, medium, and very coherent. The experiments conducted by the authors show that previous sentence-ordering-based approaches do not generalize well in this more realistic domain, with the author's baseline ParSeq that we just introduced demonstrating the best performance. Finally, to generate the trees for this corpus, we used the high quality off-the-shelf discourse parser Codra. Now we present the final results. Here, the columns denote the performance on specific genres and rows denote the models being tested. Focusing on the average accuracy across all genres, the RST-Recursive plus EDU model achieves a competitive overall accuracy at 53%, close to the state-of-the-art ParSeq. Although this lags behind ParSeq by a noticeable 2% margin, the RST-Recursive plus EDU model achieves this performance with 62% fewer parameters, demonstrating the usefulness of linguistically motivated features. Removing EDU embeddings reduces accuracy to around 50%. This is still significantly better than the majority class baseline, meaning that even by itself, the silver standard discourse structure of the document is a useful indicator of coherence. Finally, we show the results for ensembling ParSeq with our RST-Recursive, which is achieved by concatenating the document representations produced by the 2 models and passing them to the linear classifier. This approach achieves the new state-of-the-art performance at 55.39% accuracy. This simple assembling approach serves as a lower bound for the accuracy boost to be appreciated by incorporating RST features into the model. Additional results for model ablations such as recursive models utilizing only nuclearity and tree structure annotation are provided in our paper. With respect to per-class performance, we can see from this figure that coherence classifiers have difficulty predicting the medium coherence class, experiencing collapse towards the extreme ends in the best-performing models. This indicates that this class might either be not sufficiently defined or that more high-level features of the text are needed to distinguish the 3 classes. As per conclusions, we presented an approach for integrating RST features into coherence classification setting and established that even silver standard RST features lead to better results on this task. While the improvements achieved by the ensemble model are modest, they serve as a lower bound for potential gains when more accurate discourse parsers will become available. With regards to the future work, we see the following directions. As document coherence is hard to pin down to specific linguistic attributes, more data and large-scale language models might be needed to bring better results. Another direction might be experimenting with more recent and accurate discourse parsers. Incorporating discourse parser confidence in its predicted RST tree might also be of value, as low confidence might signify that the document is hard to interpret. As in the provided example, an unclear semantic connection between adjacent sentences might be another good indicator of coherence levels. Thank you very much for listening, and feel free to check out our paper and source code. Have a great day.